All right, so when we get 0 over 0, we've kind of got two methods now, right? If it's a polynomial over a polynomial, then we can factor, divide out, and then plug in. If it's factor and divide out doesn't work, and we've got a radical that's part of a two-term dude, then we can rationalize by multiplying by the conjugate. Okay, again, you don't need to know the names. You just need to know what to do and when to do it. All right, so there's another instance where we get 0 over 0, and neither one of those two algebraic methods on example 6 and 7, neither one of them work. And there's got to be another way to get rid of the 0 over 0. So this one I call the Lickum over Lickum method, which works well, of course, when you get 0 over 0 and when you have a complex fraction, which remember is just a fraction within a fraction. So let's look at example A. This one's written on with the diagonal division bar, which I'm not really a big fan of, but it's sufficient because you got parentheses around the denominator, and if you know what you're doing, you feel free to use them. But if you plug in, you get a half minus a half, which is 0 over 0. Okay, and so the bad guy that you're trying to get rid of is that x factor in the bottom. And if you look at the two terms in the top, neither one of them has an x factor in it, right? So it's not going to be the Fato method. There's no radical on either one of those, or a negative exponent, which is a fractional exponent, which is a radical in disguise. So what can we do? Well, what I think I'm going to do first is write it in this format with the horizontal division bar, the obelisk. Okay, just so you can see more of the fraction within a fraction. Okay, it turns out that algebraically, if you simply get rid of the complex fraction, that is enough to get to divide out the problem bad guy factor. But there are lots of different ways you can go about eradicating the complex fraction, and the quickest, fastest, most efficient way to do that is by multiplying by a clever form of 1, like we did in the Ratcon method. But this one is going to be the LCM over the LCM of what I call your miniature denominators. So the 2 plus x and the 2, those are like your miniature denominators. And if you want to think of this as like x over 1, 1 is one of your miniature denominators as well. Okay, your big denominator is the x itself, right? So here's what you're going to do. Think of this as an upstairs downstairs problem, and here's the main subfloor. Okay, so if you extend that out, if you want, we're going to multiply upstairs and downstairs by the same thing. So what is the LCM of your highlighted miniature denominators? The smallest thing that both 2 and 2 plus x go into. Not 2. 2 is a term in one and a factor in the other. How about this? When in doubt as to what the LCM is, just multiply them together to get a common multiple. So 2 times 2 plus x, okay? 2 times 2 plus x. That is a common multiple that you can get by multiplying them together, okay? Now, usually it's going to be the least, but, you know, not always. And by the way, multiply by 2 times 2 plus x, not 4 plus 2x. Although it's equivalent, Mason. Why? Why do we not want to multiply by 4 plus 2x, that version of it?
Because the x being 0, that's still the DNA.
There you go. Our goal, our objective is to divide out the bad guy factor, and we can only divide out factors. So if you distribute the 2, it's not going to be in that ready to divide out form, okay? All right, so now let's go ahead and work straight down the limit as x goes to 0. Go ahead and do the part that has the fractions first. And again, we did this quite a bit in pre-cal, but you know, it was a pandemic year. If you want to put that over 1, and now this is in parentheses, when you distribute this to each of these two terms, something should divide out, right? Something should divide out. So when you distribute this to the first one, the 2 plus x divides out, okay? From high to low, and all you're left with then is the 1 times the 2 that's left. 1 times 2 is 2. Now, as you do this, the fractions should be eliminated, okay? When you distribute this to the next term, the 2 divides out. And now you're left with a minus 1 times the quantity 2 plus x. And here's where that is really, really important, that you put the 2 plus x either in parentheses or you distribute the negative, okay? Everyone see what we did there? The 2 plus x divides out, so you're left with 1 times 2. And then the 2's divide out, and you're left with negative 1 times the quantity 2 plus x. And in the bottom, we just leave it all factored. So x times 2, I'm going to call that 2x times 2 plus x. Okay? That step in the top where things divide out, that's usually kind of where people get hung up. I don't like drawing lines through them because we have to use the blue thing twice, but basically this divides out with this on the first iteration. And then on the second iteration, this divides out with that, okay? If you were confused. Okay, so at this point, if you lose sight of what your goal is, this is kind of an easy mistake to make, right? Do those divide out? No, because that 2 plus x is a term in the top, not a factor. So remember, the goal is to divide out the x factor, not the 2 plus x. So when you distribute the top, let's see what we get. When you distribute the top, the negative 1, you get 2 minus 2, which that's 0. And then you're left with minus x, all over 2x times 2 plus x. Okay, so I distributed the negative there and combined the 2's to cancel them. And now, finally, we can see that the x's divide out. And we're left with a what in the top? Not a 1, a negative 1. And that's another common mistake. 2 ways you can lose that negative. It could be there on this line, but when you divide out the x's, like you take out the negative as well, or you draw such a fat line to divide them out that you kind of obscure it, or you don't distribute the negative up here. You're like, 2 minus 2, those are gone, and you're just left with x instead of a negative x. So there's lots of ways that this can kind of still get derailed. Now, normally I would work straight down, but I'm running out of room, so one more line left to right. You plug into any x that's left, and you get negative 1 over 2 times 2, which is 4. And of course, once you plug in, you don't need the limit, but as long as variables are still there, you do need the limit, right? So before you walk away, you come back and make sure you have the limit. So lick them over lick them. When you have a 0 over 0 and you have a complex fraction, this works by getting rid of the complex fraction in one fell swoop, and the bad guy should be able to divide out. All right, so whatever the function is, again, just to remind you, that function that doesn't have a name has a hole at 0, negative 1/4. All right, go ahead and do part B on your own then. Never not first, direct substitution. Never not first. If you're done, you can take a look at my work and see if I did it correctly. The red line that I have up there is me showing an unnecessary step that if you're still kind of mesmerized as to how that worked, it actually rewrites that factor, in this case in the denominator that we're distributing. If you actually rewrite it and put it behind each of the two terms that are there, then you can clearly see a little bit easier how these divide out in the first term and how these divide out in the second term. But that's a lot of writing. So if you can learn to do that mentally, it's just a lot more efficient, okay? But you never want to be so efficient that you make careless mistakes because of it, right? And again, before you walk away, make sure that if you have a variable, that you still have a limit in front of it, okay? All right, so there you go. Lick'em over lick'em, LCM over LCM. When you get 0 over 0, FADO doesn't work, RATCON doesn't work, but you have a complex fraction. This is the quickest, fastest, most convenient, efficient, and fun way to eradicate complex fractions. All right, questions on that method? All right, example 9, for lack of a better term, I call this one the sledgehammer method. It works when you get 0 over 0, and of course, none of the other above methods work. And there's some quote unquote obvious math to do. Obvious math would mean, right, it's only obvious if you see it, right? But obvious math would mean like expand things out, distribute or FOIL or something like that, okay? And this is also a good chance to introduce you to the variable of the limit, all right? So on part A, you got the limit as, what's that? H, yeah, as H goes to 0. Of x plus h squared minus x squared over h. So in this case, h is the variable, right? H is the variable. And we treat x, although it looks like a variable, right? We treat it as a constant. Treat x as a constant. And why not the other way around? Yeah, very good. The variable is defined by what's underneath the limit, okay? If that were a p under the limit, then we would treat both of those as constants, and the limit of a constant is just a constant. Okay, so if you plug in a 0 for h, you get x squared minus x squared, which is 0 over 0. Yay, 0 over 0. So the bad guy factor is the h in the denominator. But notice of the two terms on the top, neither one of them has an h, so FADO doesn't work. There's no square root on either one of them, so RATCON doesn't work. There's no negative exponents or complex fractions, so lick'em over lick'em doesn't work. But what else can you do? It's a binomial squared, so I guess you can expand it out. Very good, very good. Now, you're only going to cry, Vendelay, if you expand it out like a novice pre-cal student would, which would be x squared plus h squared. Wham, wham, boo-hoo. That's not how you do that, right? You either go off to the side and FOIL it and get the result and bring it back into the project, or you do the simple, quick little thing that is square, multiply, double, square. Okay, so how do you square a binomial? You square, multiply, double, and square. Square the first to get the first term. The middle term, which most people forget, is to multiply these two together to give you xh and then double it. And the reason is when you FOIL it, you're going to get the inner and outer product to be the same. So you'll double whatever that is, and then you square the last. So square, multiply, double, square. Square, multiply, double, square. Square, multiply, double, square. So there is that expanded. And then you get minus x squared on the back end all over h. So that's hitting it with the sledgehammer. And that was more like a framing hammer. That wasn't even that bad. But now that you've got it fully expanded, it should work out nicely. everything in the numerator now that doesn't have the bad guy factor of h in it should cancel. So make sure that it does. So I've got x squared minus x squared, and yeah. And that means now that everything that does remain in the numerator has an h factor. So now it kind of turns into a Fato method. Now you can factor the h out of any term that's left. And now the h's, which are the bad guy factors, divide out. And if there happens to be anything that's left that has the h in it in this case, you plug in a 0. And there is. There's one h left, so you get 2x plus 0, which is 2x. Yeah. And what's going to happen later on when we get into section 2.1 is you'll see then we'll let x float again as a variable, as the variable that it was meant to be. If you remember from pre-cal last year, whether you had me or Mrs. Lincoln, I don't even know if Ms. Skurhawk mentioned this, but it was what we called in pre-cal my favorite problem. Okay, this has that feel of my favorite problem. And it is my favorite problem. It's just got a limit in front of it, whereas in pre-cal, there wasn't a limit in front of it. It was just setting it up and simplifying it. So the reason that this ends up being my favorite problem is this ends up being the definition for the derivative of x squared, okay? It's the derivative of x squared, which once we get past chapter 2, you'll be able to look at that right away and say, oh, that's just 2x. You'll be able to tell it's 2x without even evaluating the limit, okay? Just like you'll be able to look at part B and say, oh, that's 2x minus 2 without even evaluating the limit. But right now you're like, what? Okay, right now it's just a limit. Go ahead and do it on your own. Do this one on your own. I'm going to work it quietly here at my desk, and we'll see if we get the same answer. Never not first, though, direct sub. Jackson, we get the same answer? Sweet. Do you have the limit on every one of your correct lines? No, I didn't think so. I'm already salivating on how many points I can dock from you on Thursday. I don't want to dock the points, but I do want to teach you one way or the other. In fact, when we get to 2.1, I'll be calling this the modified version of the derivative definition, and I'll be telling you that you're not going to have to set it up and evaluate it. Rather, you're going to be given this and you're going to have to like deconstruct it and say, oh, I spot that as the derivative of x squared minus 2x plus 1 set up. And I'm going to find the value of that limit, not by evaluating the limit, but by taking the derivative of x squared minus 2x plus 1. Okay? And it's 2x minus 2. Right. Yes. H is the variable. And so I'll plug in a 0 into that last h that's still there after I divide out. And I'm treating x like a constant all the way through until the very end. And at this point, without the perspective, we still treat x as a constant. Okay? There you go. Sledgehammer. Sledgehammer when you get 0 over 0. Now, we're going to meet a new parent function here, Senor Salta, who also goes by Hombre Trepador in certain parts of Colombia, and also known as Jumpman. He goes by lots of different names. Okay? And here's what it is. We're going to sketch the graph of the absolute value of x over x, which is identical to the graph of x over the absolute value of x. It doesn't matter if the absolute value is on the top or bottom, okay? But notice this function is not defined at 0, right? X is equals 0 is not in the domain. And what do you get when you plug in a 0? You get 0 over 0. Up to now, 0 over 0 meant that there was a hole. Well, guess what? In this case, in this singular case, 0 over 0 doesn't mean hole. It means salta, salta. Yeah, it means jump. So I'll show you why. The reason is because this is a piecewise function in disguise, okay? This is a piecewise function in disguise. Think of a piecewise function as being kind of like a primitive, a very rudimentary, or a template, if you will, for like a computer program, okay? We're going to have to tell the computer how to take the absolute value of an input, depending on whether that input is positive or negative. So let's go ahead and say if the input is positive. In a piecewise function, we put the if or whatever at the back end, right? So if the input x is positive, how would you take the absolute value of a positive number? Just the same thing, right? In other words, do nothing. Take the input x as it is. So if x is greater than 0, then the absolute value of x over x is just x over x, right? Which, of course, is just 1. Otherwise, if x, the input, happens to be less than 0, how can you manually then make a negative input positive? Well, we can't take the absolute value of it because that's what we're trying to define. You put a negative in front of it or multiply it by -1, right? So if x, the input, is less than 0, I take the absolute value of it by simply taking the opposite of it over itself. And of course, what does that simplify to? -1. And I am not defining it at 0 because 0 is not in the domain. See that? So basically, Senor Salta, the absolute value of x over x, is nothing more than a 1 to the right of 0 and a -1 to the left of 0. And what does that graph look like? I'm so glad you asked. Here is 1. It's an open circle and a horizontal line. That's what the graph of a constant looks like. And then here's -1, open circle, and it's a horizontal line going this way. And there it is. That's what the graph looks like. So 0 is not in the domain. No way, no how. Okay? You get a 0 in the denominator. But notice in this case, it is not a hole. Okay? We'll say f has a jump, not a hole. at x equals 0. Now, we're used to saying, piecewise functions are kind of the exception to most of the rules. Like, I wouldn't expect to get 0 over 0 on a piecewise function and expect it to still be a whole. But because I can basically collapse the piecewise function into a singular defined function, that is absolute value of x over x, or the other way around, this is a piecewise function in disguise, and it has a jump, not a whole, at x equals 0. So this is kind of like the exception to the 0 over 0 rule. 0 over 0, 99 times out of 99.5 means whole, limit still exists. But in this case, 0 over 0 means jump. Limit doesn't even exist, okay? The general limit. Do the one-sided limits still exist? Yes. The two one-sided limits still exist, okay? Remember, the reason the general limit doesn't exist is because 1 does not equal -1, okay? Now, this gives us a real quick and easy way to evaluate transformations of this parent function. But before we get there, let's go ahead and just evaluate then A, B, and C. What would the limit from the left of 0 be? -1, right? -1 from the left of 0, right? We start heading back towards 0 from the left, and I'm getting closer and closer to y equals -1. And by closer and closer, right, you're using your imagination there, because you're always a -1. What would be the limit from the right of x equals 0? It's 1, not because I'm getting closer and closer to y equals 1. In this case, it's because I'm a 1, I'm a 1, I'm a 1, 1, 1, I'm a 1, I'm a 1, I'm a 1, 1, 1. I'm always a 1, right? From the right-hand side. And therefore, the general limit is DNE. Now, if it asks you to justify, which it doesn't here, but if it did, you would just say, since 1 doesn't equal -1, right? As long as you had these two guys already calculated and labeled. Okay, sweet. What would be the general limit at 3, though? 1. Okay, direct substitution, right? Never not first. Okay. The only place where the limit is, the general limit's going to be DNE is, of the parent function, is at 0. So you got to be careful. Don't overgeneralize things and be like, ooh, hola, señor Salta, the general limit, DNE. No, because you're not approaching 0, you're approaching 3. 3. Cuidado, right? Be careful. Be careful. All right, now, let's look at example 11. It's one thing to identify jumpman, you know. It's another thing to identify transformations of that parent function. This is the absolute value of 2x minus 10 over x minus 5. This is not jumpman per se, is it? But let's try direct substitution. You plug in a 5, and you get 10 minus 10, which is 0 over 0. You get 0 over 0. Now, it doesn't really matter here if it's jumpman or not. 0 over 0 in this case means that the limit is going to exist because it is a one-sided limit. And whether it's a jump or a hole, doesn't matter. The one-sided limits were going to exist. Well, there's two ways we could think about this. The first way is this. Let's go ahead and call f of x the absolute value of 2x minus 10 all over x minus 5. This would be a good way to review transformations. If I factor the 2 out from inside the absolute values, I can actually pull it out front. And as long as I pull out a positive constant, I can write it like that. And then, of course, I can bring the 2 out front of the whole thing and say that it's this. Now, this would be 2 different transformations of jumpman, okay? If you take any function and you multiply in front by a 2, that's a vertical dilation. Is it a stretch or compression? Stretch, right? So the 2 is going to take any function and vertically stretch it by a factor of 2. So let's see what that's going to do with Senor Salta. I'm just going to quickly sketch the parent function. There's 1. Here's -1. The 2 is going to vertically stretch it. So now this is 2, and it looks like that. And here's -2, and it looks like that. All right. So now, instead of jumping from -1 to 1, it jumps from -2 to 2 at 0. But what does the other transformation do? When you replace x with x minus 5 for any function, what does that do? Shifts, right? Left or right in this case? Right. Right 5, a shift. So if I want to sketch what that looks like, let me use purple here. What used to occur at 0 is now over here at 5. Okay, and there's what the new function looks like. Okay, there's a jump now, not at 0, but at 5, and it jumps from -2 to 2. So once I realize that, I can look at my graph now and say, oh, what's the limit as I approach +5 from the left? Of course, the answer is what? -2. Boy, that's a lot of work just to answer that, isn't it? Yeah, it is. But at least it's fun. Is there an easier way? Yes. Okay, and here it is. You've probably already realized what's going to happen. Because the limit from either side is approaching that particular side on a horizontal line, the limit at the jump from either side is the same as the function value anywhere on that side, right? So the limit from the left of 5 is the same as the function value anywhere to the left of 5, anywhere to the left of 5, at 4.9, at 4, at -4,000, it doesn't matter. Because it comes in as a horizontal line segment from either side, the function value anywhere from that side is the same as the limit from that side. So here's what we could do in the future. As long as you plug in and get 0 over 0, and you realize it's a transformation of Senor Salta, which, how would we recognize that? Well, yeah, it's got the absolute value of mx plus b all over cx plus d. That is the absolute value of linear over linear, or it could be flipped around. It could be mx plus b over the absolute value of cx plus d. As long as it's linear over linear, okay? X to the first over x to the first. And one of them, top or bottom, has the absolute value. Then, as you plug in and get 0 over 0, you're approaching the location of the jump. All you have to do to figure out the one-sided limit is plug in any value from that particular side. So let's see. If I wanted to do this again without the graph, let's just kind of get this out of the way now and pretend like I don't know it's -2. I'm approaching 5 from the left. Well, never not first, direct substitution. I get 0 over 0. Ah, okay. I have the absolute value of linear over linear. Ah, okay. Hola, Senor Salta. Pick a number now that's to the left of 5. 4, okay? Let's plug in a 4. Direct substitution. The absolute value of 2 times 4 minus 10, all over 4 minus 5. What does that give me? That gives me 8 minus 10, that's -2. The absolute value of -2 is +2, all over -1. And of course, that's -2. It worked. You don't want to plug in a 4, you say? You want to plug in a 0? Okay, let's do that. That's the absolute value of -10, all over -5. Hey, that's -2 also también as well. Yeah. Okay. Now, that little trick of plugging in any number from that respective side only works on Jumpman. You can't start doing that with like other things, right? Like, oh, this function has a hole at x equals 0. So I'm just going to find the y value of the whole by plugging in a negative 200. No, that only works on Jumpman, and it only works on Jumpman because two horizontal lines coming in, okay? Now, if it happens to be a general limit, and you recognize that it's Signor Salta at the jump, then it's DNE, right? And it is DNE. Left side doesn't equal the right side, okay? All right, so go ahead and let's see what B is going to be. Limit as x goes to 5 from the right. Never not first, direct substitution, you get 0 over 0. Pick a number bigger than 5. 600, very good. I'm going to choose 6, though, okay? 6 times 2 is 12. 12 minus 10 is 2. So I get the absolute value of 2 over 1. Hey, that's just 2. If you knew the left side was negative 2, could you then just assume that the right-sided limit would be positive 2? Is it always symmetrical like that? It will be, yeah. If it's just linear over linear, and there's no vertical shift to Jumpman, which you could technically separate as just its own separate limit, yeah, it's always going to be at 2 symmetrical limits. All right? And then what would be the general limit here at 5? DNE. Or negative infinity, or just DNE? Only DNE. Or non-existent, right? DNE. DNE, 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 DNE. Okay, cool. Now, are they always going to be that easy? Probably. Can they get extra spicier than that even? Yeah. Watch this. Example 12. Evaluate the following. The limit as x goes to negative 3 from the left of x squared times the absolute value of 2x plus 6 over 4x plus 12. Never not first, direct substitution. If you plug in a negative 3, you get 9 times the absolute value of 0, which is 0. 9 times 0 is 0 over 0. Hey. Is this a transformation of Jumpman? Yes and no. Do y'all see the Jumpman piece? Yes. Not only does it have to be linear over linear, but it has to be the 2 linear pieces that cause the 0 over 0. This is causing the 0 in the top. This is causing the 0 in the bottom. That's linear over linear. The top one has the absolute value. That's the Jumpman piece. What is x squared causing when you plug in a negative 3? A 9, right? So can I just plug in a negative 4 to this entire expression to figure out what the overall limit is? No. But can I plug a negative 4 into the highlighted piece to figure out the one-sided limit? Yes. This is where the properties of limits from 1.2 come back. The limit of a product is the product of the limits. So as long as I can isolate the Jumpman piece, I can evaluate it that way, but only that piece. So here's what we could do. The limit as x goes to negative 3 from the left of x squared times the limit as x goes to negative 3 from the left of Signor Salta. Right? We can reproduce the limit. Now, if you just saw this piece here, you would not try to evaluate that limit by plugging in a negative 4, would you? Or a negative 5. I'd be like, what are you, crazy? We're approaching negative 3. You would use direct substitution. You still have to do that. It's negative 3 squared. But how would you evaluate the next piece? Plugging in something smaller than negative 3. A negative 4, a negative 5, but only that piece. So let's see what we get. I'm going to plug in a negative 4. I get the absolute value of negative 2 all over negative 16 plus 12 is negative 4. So this becomes 9, and then that becomes 2 negative 4ths, which is negative 1/2. And so this becomes negative 9/2. If you were to plug in a negative 4 to both pieces, the Jumpman piece and the regular old smiling parabola, you would get negative 16 halves. Because you wouldn't get 9, you get 16. And guess what an answer choice would be on a multiple choice? Negative 16 halves, or negative 8. So, cuidado, cuidado, right? Okay, have a fantastic lunch.